So we want to talk about separation of concerns with Docker and containers, and I will explain what this means. And if I move here, I think you won't hear me anymore, so I should remain around here. So short intro, I'm Jérôme Petazzoni. I work for Docker. I work for Docker even when it was not Docker yet, so I'm a kind of hipster of containers because I was doing that even when it wasn't cool yet. So back in the days when I started with containers, I was working on .cloud. That was platform as a service. We started that almost 5 years ago, and we're using containers in production at scale. So I picked up a few tips and tricks about running containers. So the intro for today is that the outline for today is that I want to do an extremely short intro about Docker because I guess you already know a lot about it. So I don't want to get it to be too boring to like explain what is Docker since most of you already know. But I will try to drop some bits of useful knowledge during this intro to make that interesting nonetheless. Then I will talk about some of the differences between VMs and containers. And the goal is not to make like, oh, containers are better or worse because this and this. The goal is to see from those differences what kind of things we can extract to build something that I will call lean containers, so that are containers that have just what we need, and then we can add other containers next to them to implement extra features like logging and backups and monitoring, all the things that you don't typically need in development, but that you need in production. So let's do this. First, quick recap about Docker and containers. As you probably know, the Docker motto is like build, ship, and run any app anywhere. And I decided to break this down to see exactly what it means. So first, build means take any Linux program and put it in a container. Can you raise your hand if you already know that you can take like web apps and other services and put them in containers? So virtually everybody, of course. You probably maybe also know that you can put data stores in containers. Less people, so either people are tired or raising their hands or something. But yeah, you can put data stores in containers as well. Other stuff like console, etcd, RabbitMQ, Zookeeper. Anybody doing that? Not a few? Yeah, okay. Command line tools, for instance, the Amazon command line. Each time I need to do something with that, I end up having to install, it used to be Java, now it's some Python stuff, and it's kind of boring. Now I can run that in a container. So when I need to install something on the command line, I can install a container instead. Does anybody here does that already? A few people? And now something that you probably don't know unless you happen to see Jessica Frazel's talk at Container Camp in San Francisco or other stuff like that. You can put desktop applications in containers. Anybody doing that? A few persons, great. Yeah, you can actually put like Chrome, OpenOffice, Skype, Steam, all that stuff can run in containers. So down the road, I think we will end up having pretty much everything in containers. What about non-Linux programs? So you can also put Windows applications using Wine in containers, and that's actually a pretty good way to deploy them because Wine is a kind of tricky thing to set up, but if you put that in a container, then you do the hard work once and put that in a container, and that container can work everywhere. I'm pretty sure that nobody really saw that coming. One thing that I absolutely did not see coming is Docker on Windows, and a couple of years ago when I was doing the first talks about Docker, I was joking about the fact that there would never ever be Docker on Windows. Turns out I was wrong, jokes on me, because Microsoft is working on that. They made some pretty cool demos at Build, I think, last month. And so Docker on Windows is coming. There are people working on a Docker for FreeBSD port as well, and there is maybe someday Docker for OS X, because at that point, when you have Docker almost everywhere, why not get it on some of the most popular developer environments today? So then the second part of build, ship, and run is ship. So with Docker, we can ship those containers easily by breaking them down in small layers and shipping only the layers that changed. So that makes it easier to ship containers compared to VMs, because instead of shipping a 10 gigs VM image, we can ship smaller layers, and that's much faster, especially when you don't have a super fast fiber coming straight to your development machine. And the last step in build, ship, and run is run. So containers give us a way to run both on physical and virtual machines, so that's great, hybrid cloud and things like that. Docker is available on all modern Linux kernels. That changed quite a bit since like 2 years ago when Docker only ran if you had Debian or Ubuntu kernels with AUFS. Most cloud providers today have several images to run Docker. There are distros that have been made like from the ground up just for the sole purpose of running containers, like Atomic, CoreOS, SnappyCore. RenShareOS is also pretty cool. Almost 2 years ago, I remember talking with some Rackspace folks about, hey, it could be nice if we could use like Docker as PID1, Pipedream and everything. Turns out that RenShare Labs did that, and RenShareOS is actually a Linux distro where Docker runs as PID1, among other nice things. There are other Docker implementations available. There is Joyent, the people that are kind of still maintaining Solaris and all that amazing stack, have something called Triton, which is part of their smart data center thing, and that lets you run Docker containers as Solaris zones. So the code base has almost nothing in common with the Docker code base, but the API is the same, so you can point your Docker client to that and run containers inside Solaris. And there are many Docker as a service things that are appearing every day. I think yesterday or 2 days ago, there was ProfitBricks, I think, who announced that they were launching something to host Docker containers as well. Anyway, so let's talk a little bit about the differences between VMs and container. And I want to stress out that the goal is not to make like a kind of scoring card, but rather to see what kind of different beasts VMs and containers are, to see how we can leverage on those differences to make something really cool. From a portability point of view, containers can run pretty much anywhere. So if I have a container, I can deploy that on EC2. Contrast to when I have a VM, if I want to deploy that VM on EC2, that's kind of complicated, because even if technically today we can run VMs within VMs, like nested hypervisors, those things exist, but it's not really easy to do that on EC2. I'm not going to say impossible, because then someone will tell me, no, we did it, but it's hard enough so that if you look for it, the answer is not obvious. So containers give us at least something that we can move around really easily. From the format point of view, I wanted to make a kind of, not really a comparison, but more like let's try to map concepts between VMs, as in like PC virtual machines, the JVM, the Java Virtual Machine, and containers. You can imagine that a VM is something that executes machine code, and its environment, so the way it interacts with outside world, is something that looks like a computer. So it pretends to have maybe a PCI bus, and there is a network card sitting on it, and there is a video card, and there is this and that and that. And little by little, we try to strip away all those things because they just added a lot of overhead without any interesting feature. If we contrast with the JVM, for instance, the Java Virtual Machine, what the JVM executes is Java bytecode. It's not Intel or other machine code. And the way it talks to the outside world is using the Java APIs. Now, if we compare that to containers, with containers, we are still executing machine code. And in the case of Docker, we would say, okay, it's going to be Intel 64-bits machine code and nothing else officially. And the environment is the ABI with the Linux syscall interface. That's pretty interesting because those two things, the Intel 64-bits instruction set and the ABI used to talk to the kernel, are extremely stable. They are extremely stable because Intel is not going to change their instruction set overnight because suddenly they would break compatibility with everything, so they don't want to do that. And the Linux kernel syscall interface is also pretty stable because whenever someone changes it, either voluntarily or by mistake, they get an email of, list of profanity by Linus Torvald himself about how they're stupid and they should just stop programming and go somewhere and die. So nobody really wants to change that because it kind of hurts to receive that kind of email. So those things are pretty stable, and it means that containers we do today will probably still run in 10 years. Right, from the overhead point of view, containers are just normal processes running on top of a normal kernel. The only thing between a process in a container and a process not in a container is a few labels on top of the process to say this is in container X. But when a process is not in a container, it still has those labels, except the labels say this process is not in the container. But the code path, whenever the container is reading from disk or sending something on the network or doing some computering or whatever, the code path is exactly the same. So the performance will be exactly the same given that you tune the proper things. The context switch between two containers is exactly the same as the context switch between two processes. So that helps a lot for people who want to have bare metal performance. Right. On the other hand, VMs don't have that, but they have a much stronger isolation because VMs are not, well, they are processes running on the kernel, but inside the VM, that's where you do your things. And when you want to get out, you have to go through the number of drivers and the hypervisor, and ultimately that runs on a non-privileged process. So even if there is a critical security issue in your VM and you manage to break out of the VM, you end up being a non-privileged process on the host, and from that point you have to start your attack all over again. It's a little bit like when you're in a prison and you break out of the prison and you realize that you're on the moon and you have to build a ship to get back to Earth. That's pretty much what happens when you can break out of a VM compared to a container where if you can break into the kernel, well, then it's game over because you escalate to the whole machine, and from a security standpoint, that's not cool. So, however, this means that when VMs need to communicate between each other, they have to use the good old TCP IP stack because there is no direct path between VMs. So again, there are some hypervisors that will provide some direct communication path, but this is pretty rare. I don't know of any public cloud that exposed them. And even if they did, they would be different between, for instance, Xen, VMware, KVM, and so on and so on. Like Xen has something like ZenBus, so you can do some really fancy thing and achieve super high performance between VMs, but that's specific to Xen. Containers, on the other hand, can use normal sharing mechanisms. We can use sockets, like local Unix sockets. We can share bits of memory. We can even, like a container can even see and access the processes of another container directly if you allow that. So that's much easier. And this leads to this kind of comparison. If we were to explain how containers and VMs are different, is that VMs are like brick walls. That's solid. It's pretty hard to knock down a brick wall, except if you're a ninja and you have mad skills like that. But it's pretty slow to build. If you want to move a wall of bricks, it's going to take some time and be pretty messy. However, a container will be a kind of a room divider made of rice paper. So it's pretty easy to set one up. It's pretty easy to move it as well. However, it doesn't provide much security. That's the kind of first thing we think of when we see those. So it's like, okay, containers are not very solid, but at least I can move them around extremely easily, and I can do that with VMs. At the same time, those kind of lines are blurring now. VMs are not exactly those unmovable walls of brick, and containers are not those frail room dividers. There are a few initiatives, like Intel has done something called Clear Containers. There is a PaaS company in France called Clever Cloud that does something pretty similar, and basically they kind of removed things from VMs. They try to look, okay, what happens when we start that VM? Why is it taking so long, as in hundreds of milliseconds as opposed to milliseconds for a container? How can we make those VMs so that they look like container, as in like they would start super fast, they would take a very small amount of memory, and they did it. They made VMs that are not as fast as containers, but they are really getting close. And at the same time, there are people who say, well, we're not happy with the status quo about container and security, so we want to make extremely secure containers. So there is, like Joyent I was talking about, they managed to get Linux binaries running on Solaris zones. Solaris zones are extremely secure, and so now you get a way to have secure containers. Another way is to use Linux native security mechanisms like SELinux, Palm or GRSec, and then you get something that's also pretty solid. So now if we kind of leave the technical differences and look more about the functional differences. So what are the differences in workflows, in uses? How do we handle containers? How do we handle VMs? So a VM will typically need everything inside it to work, to function properly. You need a full OS, you need a kernel, you will typically have cron and syslog and some backup tools, and well, it's a kind of a self-standing thing. With containers, on the other hand, there has been a lot of things written about machine containers versus application containers. Machine containers are kind of lightweight virtual machines. They have an init process. They run all the usual suspects, SSH, cron, syslog, etc., while application containers will run your application as PID1. If you want to run MySQL, then MySQL is PID1. If you want to run Apache, Apache is PID1, and so on and so forth. Those containers need a lot of help from the outside because they don't have anything fancy for logging, they don't have anything fancy for remote access, and so on and so on. So they need some kind of support from the host environment. The lifecycle now. With VMs, the kind of classical approach is you bring up a VM and then it will live, maybe not forever, but at least for a very long time. It will be updated and we will put new versions in it, and that will introduce something called configuration drift. Configuration drift is when I have a server that I deployed 1 month ago and it's supposed to have exactly the same software as a server I deployed a few days ago, but in fact, during that time span, there were some packages that were updated. Maybe the base image that I'm using on Amazon or Linux or Rackspace or whatever has changed a little bit. And so this drift at first is not extremely severe and has minor effects, but over time it gets bigger and bigger until suddenly some stuff works on a machine and not on the other. So to avoid drift, one of the answers is to use configuration management. That's often pretty complicated and that doesn't solve all the problems. So another idea is to use golden images. And with golden images, you might have already heard those either as golden images or Phoenix servers, immutable infrastructure, immutable servers. The idea is that you have templates, you have images for your servers, and when you want to make a change, even if it's one line of code somewhere, even if it's a silly, tiny CSS change, then you bake a new image, you start new servers, and you destroy the old servers. So that seems a little bit extreme, but that avoids that configuration drift, that avoids a lot of problems. On the downside, even if that's nice and clean, that's also pretty heavy to set up. And people like, typically Netflix and Amazon tell you, we do like this, and it's awesome, it's great, but they have the tooling and the scale, and they can kind of afford to do that. Smaller shops can't always say, okay, sure, we're going to destroy everything and recreate everything each time we change one line of code. It's not always as easy. Containers have this kind of best of both worlds approach where we always create them from an image, but image creation itself is super easy. It's super easy to create new container images, and then it's really easy to switch from the old image to the new image. So why is that? Why is it easy with containers and hard with VMs? It just boils down to the time it takes and how convenient it is to take a snapshot and create a new instance. Like if you've used already like Docker with Docker files, you do that all the time when you build a Docker file. When you have a Docker file with 10 lines, you're creating 10 containers. Each time you're creating a container, you're doing something in it, taking a snapshot, so that's the new image. And then with that image, you're creating a new container, executing the next line of the Docker file, and repeat and repeat and repeat. If you do that on EC2 with VMs and EBS, so you create the VM, then you wait maybe 1 minute or two, and the VM is up. 1 or 2 minutes is not too bad to provision a VM, find the resources, boot it, and everything, but it's still 1 or 2 minutes. It's not like the half a second it takes with a container. And then you do your thing, and then you snapshot the VM, so it's API calls, and you wait for the AWS API to tell you, it's okay, I've done the snapshot of this VM, then you start a new VM with that snapshot. So basically, a build that would take 5 seconds with containers would take probably something like 1 hour with VMs. And that would be for a pretty simple build, not like a super complicated, crazy one. And that's not because VMs are slower or whatever, it's just because the machinery and everything is way more complicated. We have to do API calls instead of, and those calls are slow, instead of immediately doing a snapshot and creating a new container. Now let's look at the development process, and we are getting to the meat of the issue here. The best practice is when you go like SOA or microservices is you will put your different components on different machines. You will have your web tier, and that's a bunch of VMs. Then you have maybe your API that will be on another bunch of VMs. Your database will be running somewhere else. You have a bunch of workers, that's something else, and so on and so forth. If you want to replicate that in dev, that would mean having one VM per component running on your local machine. If you have nice local machines with 32 gigs of RAM, it's kind of okay to have a dozen of VM. However, if you have smaller machines, or if you have kind of pushed the microservice approach to the extreme and you have 200 or 300 components, you certainly don't want to have 200 or 300 VM running on your laptop. So with that means that you will have a significant difference between your prod and dev environment, because in prod you will be running on so many virtual machines, and in dev you will have typically one VM and it has a bunch of components inside, but the deployment will obviously be different. In prod, you also need a lot of extra stuff, like you want to ship your logs to Splunk or Papertrail or Loggly or an ELK cluster. In dev, you generally don't want to do that. You just want to have an easy way to check the logs to see what you're doing, but you don't want to have the same heavy machinery. So again, this means very different environments between dev and prod. So with containers, at least we can run many containers on a machine, so we can have the same containers in dev and prod. But how do we provide container variants? So how can we make it so that in production I'm shipping my logs to Splunk, but in dev I'm not running the Splunk collector and all that stuff. I just want logs in the local file and grep and tell and do that to them. So there are a couple of approaches. The first one is kind of bloated containers. So it means you put everything you need in your containers. So you end up with a kind of Frankenstein-esque container that has your application, but also maybe New Relic or Datadog or Splunk or all the things that you need in production. So that's a huge container, and it's supposed to start like many processes. The problem is that the behavior will be different, because locally you just start, let's say, Gunicorn for your Python app, but in prod you will start many other additional processes, and you can end up with, well, it doesn't work the same way in dev and prod because of those processes, because maybe this monitoring thing is doing something to the app, or it's binding on a port, and so my app can bind to it or whatever. And it also means that it's kind of hard to decouple things, because now in my application container, I also have to put the backup process. Like my ops team told me, you have to install this backup thing and set it up that way and that way. And so it's kind of risky, because as part of my development process, I might break that. And when you break the backups, bad things eventually happen. So the other approach is to use lean containers. And the idea is to stick to this Unix philosophy, do one thing, but do it well. So we stick to one container with whatever you're working on, your component, your code, or your database, or whatever, and then have separate containers for everything else. Logging, monitoring, backups, debugging. So how do I analyze network traffic? How do I check latency? And so on and so on. So how do we do that? The idea is that, as I said earlier, with containers, we can share a lot of things between our containers. We can share files, we can share network stacks, we can even share memory space, and that's what we will use. So for instance, let's look at logging. There are kind of two ways, well, at least two ways to do logging with this lean containers idea in the case of Docker. The first idea is to have your containers write on standard output, and Docker kind of collects these standard output messages, and it will send them either to local JSON files or to syslog. There was in Docker 1.6, I think, the addition of logging drivers, so you can kind of decide where you want to send the fire hose of logs generated by your containers. It's not yet perfect. Like if you decide to send your logs to syslog, then you can't use the Docker logs command anymore. But the hooks are there, and down the road, eventually, we know that it will get much better. Meanwhile, another solution, if you have something that insists on writing a bunch of local log files and doesn't want to go to standard output, which is pretty reasonable because most web servers will write like an access log and an error log, for instance. In that case, fine. Let's use something that we call a volume. So if you already know Docker well enough, you're familiar with volumes. Otherwise, volumes are directories that are shared between the host and the container. So it's a kind of mapping, a pass-through between the container and the host file system. So here you can start a container, so that's my application, and I'm telling to Docker, hey, /var/log should be a volume. Make it so, make it happen. So right, when I do that, Docker will allocate a directory somewhere on the host, and it will map it to /var/log in the container. And then I can run another container, and I will use the volumes from option that tells to Docker reuse the same volumes as the first container. And in that container, I will run something like tail-f var log everything. So that's like the simplest way to get the logs out in that case. But if I want, I could just get a shell and manually run tail and grep and awk and whatever I want. If those are HTTP logs, I could have another container in which I install Apache Top, which is a pretty nice tool that kind of gets the HTTP logs as they come, and that gives you the top requests showing up in those logs. So basically, any kind of custom tool that you might need will be in that container instead of being in the application container. So instead of having the application container that ends up being a gigantic garbage bin full of all the tools that everybody that worked on the application installed one after the other, you still have a very simple and lean application container, and everybody has their own little toolbox on the side when they need something. And now when you run in production, you could have a log collector container. So this one could have anything. It could be the Splunk agent. It could be something that tails the log and sends them on RabbitMQ or on Redis PubSub or whatever you want. The application doesn't have to know anything about that. The application just puts the log files on var log, and then that log collector picks the logs in that directory and sends them wherever you want. So that's exactly what I just said. Other upsides are that if you're running some really custom and let's say expensive log analysis, expensive from a CPU or memory point of view, you can isolate that from the application itself. For instance, if you have something that counts unique visitors in log files, that tends to use a lot of memory because you have a pretty big data structure with like the fingerprints of each visitor, like IP address, browser, things like that. Then running that kind of log processing can eat up like tons of memory. And if you're particularly unlucky, you can eat enough memory to take the web server down because the logs will be on the same machine. If you run that in a container, then you only take the log analysis container down instead of taking the web server down. And the last advantage of that system is that if you, at some point you decide to move from one logging system to the other, that's extremely easy to do. You just have to change that logging container instead of changing the application container. So sometimes people ask about what's the performance overhead of this? Like, because I'm sharing data between two containers, is there a protocol involved? Is there some latency? Is there anything? No, there is nothing special. When two containers are accessing the same volume, it's exactly just like when two processes are accessing the same directory. So there is nothing special to do. It just works. It's a direct path to the underlying file system. And there is absolutely no overhead when multiple processes are accessing those files. Same thing for synchronization. The data immediately shows up when it's written by your web server, for instance, because it doesn't have to be transferred anywhere else. It's just like when you write to a file, if you read back that file immediately after, the data is here. So it's the same thing here. There is nothing to synchronize because there is really only one copy of the data. Let's talk a little bit about backups. Exactly the same idea. When you want to back up some files, it could be like here I deliberately picked like /var/lib, so those could be database or pretty much anything. Often we have extra tools to ship the files outside of the servers. Maybe we're backing up to S3, so we have S3 CMD or Bodo. Maybe we are backing up through a remote server with SSH. So in that case, we have not only SSH, but also some key material. Maybe we're using rsync or Unison to do like multi-way synchronization. In that case, once again, let's put this data in a volume and let's share that volume with another container, and let's have all those custom programs in that other container. That way, and I'm sorry, but I will kind of repeat that to make sure everybody gets the point, but the application container only has what it needs. It only has the application itself, and all those other functions are in separate containers. Right. Another example, when your backup is network-based, so as opposed to I'm taking those files and I'm putting them somewhere, network-based backup here means I'm connecting to the database or to the API and I'm extracting the data, and then once I have that dump or that extract, I put it somewhere else. So it's exactly the same thing. I have a separate container to do that. And the main advantage here is that the responsibility is now kind of split between two teams. There are people working on the application container, and so maybe that's an API, and we want to have something that talks to the API to extract data and save it somewhere. If you put that backup kind of thing in the application container, now it means that it's the responsibility of the people maintaining that container to make sure that the backup script is still running. However, if it's a separate container, then you can say, okay, there are people maintaining that application container, people maintaining that backup data extraction container, and if people working on the app kind of break the backups, well, first, they won't make a mistake like, oh, we accidentally commented out the cron job because it's not their cron job anymore. Now the cron job is elsewhere. Or, oh, we accidentally removed cron, even worse. Or we replaced it with something else. Or, no, now it's something separate. And in addition, instead of having some, let's say, entanglement, because you have that dev team that says this is the container with the API and with the backup script, and then the ops team has to check that everything is fine before kind of green lighting that container for production. Now the dev team can go with that, and separately the ops team will have their backup mechanism, and if something is broken, the ops team realize it instead of having to constantly after each deploy look for it. So it sounds a little bit like the microservice approach. Like, you know, instead of having one gigantic code base and everybody must deploy in lockstep, like it's deployment Wednesday. So for Wednesday, everybody must have everything like in a shippable state. When you move to microservice, instead you can say, well, everybody ships whenever they can or want. We have little separate components, and that way, if there is one component that needs to ship like every day, and another that is going a big refactoring, and so for 10 days they won't be able to ship because they are breaking things. With microservices, you completely dodge the issue by deploying separately. So here is the same idea. We apply the microservice framework and ideas to dev and ops tasks. Another example, let's say you want to do some network analysis. You want to investigate like packet loss or latency or some really weird requests that you don't even show up in your HTTP logs. Usually the tools that you want to use are things like TCP dump or ngrep, ntop. If you want to check like number of ongoing connections, you can use netstat or SS. The problem is that you typically end up installing those tools in your servers, and that's exactly like the log analysis problem of earlier. It's like over time, your servers end up having tons of tools with different versions. Like somebody will be investigating something with TCP dump or ngrep, and then when they go to another server, it's like, oh, it's not installed, or worse, it's installed but it's a different version. So I did packet captures from different machines, and then I consolidate them, and it doesn't work because the format are slightly different. That's a nightmare. So here, instead, we can share the network stack between containers. So I start, for instance, an Nginx container, and then I use, so it's Docker run, and the option is --net container, : and then a container name or ID. That means run a new container with its own file system, process space, memory, yada yada, but reuse the network stack of that other container. And so when you do TCP dump, you will see traffic showing up on Nginx. If you use SS to see the open sockets and are they like in the exact state, like con wait, fin and everything, you will see the sockets of Nginx instead of the sockets of an empty container. Service discovery, that's when it gets really exciting. So Docker can do some linking of containers, which really means DNS injection. And the idea then is that your code just connects to, say, Redis, if you want to connect to a Redis service. And it behaves like, I mean, your container wants Redis to resolve to some IP address. And then Docker does exactly that. It will inject a DNS entry, which is a fancy word for adding a line into /etc/hosts, so that Redis resolves to some IP address. It can be the IP address of another container, or it could be the IP address of a remote Redis service. So the idea is to, in dev, to use Docker Compose to automatically kind of stage that for you. And when moving to production, use something slightly more complicated, but that will, again, not change how the application behaves. So technically, that's the pitch about ambassadors, and you probably have it already, but when you want to link together two containers that are running on different machines, first we start container B, so let's say that's Redis, that's the thing we want to talk to on the Docker machine, and then we get the host and port that it's using. Okay, maybe we put that in console or etcd or wherever, and then we start the ambassador that is actually just a relay. It's something that will accept connections and it will just like send back those connections to the actual service. And then we start container A, the one that wants to connect to Redis, besides the ambassador. So we end up with Redis somewhere, and then elsewhere there is my web app that wants to connect to Redis, and just right next to it there is this ambassador that will relay traffic, but also handle discovery, like where is my Redis, and also failover if you want to add that kind of behavior. And the key idea here, it's not to magically solve a problem, because you still have to deal with load balancing and discovery and failover and all those things. But at least you don't have to do that in your application code. Your application code can just connect to Redis without having to think twice about it. And then that Redis thing is the ambassador that deals with the details. Okay, so again, the idea is to kind of enable separation of concerns. Devs do devs, ops do the network plumbing, and we think that's great. Composition of stacks of containers, and that's the last part. So you might have heard about Docker Compose that lets you kind of describe a stack like this. So that's a YAML file, and for each service, you have a section describing how it should be built, should it use an already built image, and so on and so on. And this file can be kind of transformed. So I'm currently working on a workshop about advanced Docker orchestration, and so I use this, that's an actual microservice-based application, and then it's transformed into something like this. This is a kind of close-up on one part of this Compose YAML file, where initially I only had the worker and the hasher. And now, in fact, the worker, instead of connecting directly to the hasher, connects to a hasher proxy, and the hasher proxy is an ambassador that connects back to hasher. The idea is that, okay, writing that kind of YAML file manually would be tedious and kind of annoying. However, it's YAML, and the input and the outputs are pretty simple, so it's actually pretty easy to generate that with very simple scripts. So that's one of the, you can expect like this YAML generation and this whole process of setting up ambassadors and everything to happen automatically down the road. But for now, if you need to do it yourself, that's pretty easy. About Docker and networking, we just cut out Docker 1.7 RC2 yesterday night. So you can expect 1.7 to be like released anytime soon. Among other nice things, Docker 1.7 will add networks as a first-class object, which means that you can define networks, you can put containers on networks, and those networks can span multiple Docker engines, which will give us other ways to connect those containers like that. But even in that scenario, the key idea remains, which is that your application just connects to Redis and doesn't have to know that Redis is actually a local container or maybe an ambassador, or maybe it goes over this new network abstraction or whatever. No, the app doesn't have to know that. The app shouldn't know that. Right, so conclusions. Containers can share more context than VMs. We can share files, we can share network, we can share all those things, and we can use that to decouple complexity. So I like to think of that about just like microservices, but instead of being this is the data layer, this is the API, this is this and this and this, it's more this is the dev team, this is the network team, this is the storage or backup team. So now we have not only multiple components, but also multiple layers of responsibility in the organization, and then can work independently instead of being in lockstep, like, okay, before going to production, we need the green light from the ops team to make sure we didn't screw up anything. All tasks that used to require VM access can be done in separate containers, and the result is smaller, leaner, simpler containers. And those tags can be expressed as simple YAML files, so that's also simpler than it was before. And the kind of the last thing I want to state is that sometimes people think that Docker will solve all their problems because after the first experience, it's like, oh, it builds stuff, it's great, oh, it's amazing, and oh, well, actually, it doesn't do all the things I expect it to do. There is no magic. Docker will not solve all those problems for us, but it will give us really powerful tools to solve those problems more efficiently. So that's not something that would build your IKEA shelf for yourself, but it's a really powerful electric drill so that it's much less hard to do it, if you will. That's it. If you have questions, I think we have about like 10 seconds to answer them.
Yeah, I have a couple of more. Let's run over. Don't be shy. Free t-shirt.
I do have a question. So within the network stack, is that a passive knowledge? You had described the network stack. Is that a passive monitoring tab, or can you inject packets into it?
So the network stack, the thing that's upcoming in 1.7, the idea is to first have this kind of concept of networks, and then, well, by itself, I don't think we want to expose like an API thing so you can inject packets, but if you want to, you just have to start a new container that sits on this network and then we'll inject packets. Does that make sense? Cool.
This was actually the previous example where you were doing a TCP dump or what, I didn't know, was that just for passive monitoring?
So, right, you can do both. So for the example I gave with like, let's run TCP dump in a container that shares the same, but you can also inject packets. You can do pretty much anything you want. It's exactly as if you were in the same container from the network point of view. It's a different file system, it's a different process table, but it's the same network stack. You see the same interfaces, the same IP address, the same IP tables rule, the same routes, the same everything, but only from a network standpoint. Thank you.
Thank you.